It's Mark Cronin from Liverpool John Moores University, and I'm just going to illustrate how, or it may be possible to use the type of information that we're gathering within the context of read across. So I'm going to discuss, very briefly recap. Stephen Enoch has introduced what read across is, and then what's gone on within Cosmos, and then also within Seurat. And just to emphasize, I'm dealing strictly in our, what we talked about before, in our prediction of effect at this point. And this is the process of data gap filling, and this is a slide nearly all of us will have seen many, many times before about the definitions of read across and interpolation. And this sums up particularly what Steve Enoch was saying, that if we can group some compounds together, we have some data, then we may be able to read across from known data points to other data points. And it sounds a very simplistic way of doing things and a very straightforward way. And of course, it's seldom that simple. Like it or not, this is now a reality. And this is just taken from the ECHA report from last year, which outlined the number of read across studies that in this case were submitted for developmental toxicity. And read across is the light blue at the bottom, and it basically accounts for something like a third, 1 in 3 of pieces of information provided in REACH submission dossiers. And that is expected to increase. So people are using read across. And the reason why, well, the advantage is, as we've heard, the read across approach is transparent. One can see clearly, should it be documented correctly, that why the read across approach can be used. We have freely available software, not only the types of software we've been talking about, but most famously the OECD QSAR toolbox. And it has the possibility of regulatory acceptance, and we'll come back to that point. Disadvantages, well, as we've heard and indicated, it certainly requires expert judgment, and it requires skill in the documentation, description and justification of a read across. And the key problems are defining and justifying similarity, so stating and being able to justify definitively that two molecules are similar. Doing this particularly for the endpoints we've been talking about today, as well as developmental and reproductive tox. And as has been alluded to either in the comments or in the discussion, the issues of proving low or no toxicity. So the read across and structure activity approach is very good at confirming a compound may be toxic, but much less so currently, the current way it's set out, for defining low and no toxicity. And the other issue is we're still not certain, although we do have increasing feedback from ECHA, what the actual acceptance of read across predictions is in terms of regulatory acceptance and also internally for industry use. And this summarises, I hope you can't see this on the webcast, this summarises part of the problem. When are two similar things really similar? So Steve uses cuddly lambs and bananas. I go to the north end of Liverpool where life is hard rather than the south end. And if you want a slightly better illustration of the problems, here we have, of course, the issue of thalidomide, and these are, in terms of way we may describe chemistry, if we describe it incorrectly, identical molecules, but of course we have the isomerism issues. And that is the level of subtlety in which we need to be able to define our levels of similarity. So Steve alluded to this, not at this level of similarity, but this is, if you want to destroy the whole read across paradigm, this is one of the examples you give. And there are many similar of these examples. These are termed activity cliffs. And these are useful to us because they help us define our domains. We can see a cutoff and we can understand it in terms of mechanism of action. So illustrating the point of grouping, this is just a very simple, straightforward series of molecules. And and it forms one of the groups that has been considered, at least in passing, in surat. Here we have allyl alcohol, and that's a direct-acting electrophile, so one could consider a whole group of molecules that, to the untrained eye or to molecular similarity software, may be classed as similar, but it's not until we go to the level that Steve Enoch was considering in the detail that we can begin to understand which of these may be toxic. So of course allyl alcohol is metabolized and it becomes an electrophile, and molecules that have that same functionality are highlighted there, the two on the top left, and they have the similar molecular structure. So we would predict those to be, according to this paradigm, we would predict those to be liver toxicants. These molecules we would predict not to be toxicants because they lack the chemical features that transform them into an electrophile. This compound at the top right with the dash, I'm not sure, we're unsure about whether that would be a toxicant or not. And the compound in the bottom right-hand corner with the triple bonds, because of the activating nature of the triple bond, that would be an even stronger toxicant. So we begin to rationalize this in terms of chemistry. Now, of course, what we want to be able to do is back that argument up with something. We can say they're similar or dissimilar in this case in terms of chemistry, but how can we prove that? And this is one of the linkages to the AOP concept. So this is just captures the draft AOP for fibrosis, which those allyl alcohol is associated with from the European Commission's Joint Research Centre. And our modern paradigm, of course, is to be able to use this information to devise tests and answer the question, how is the AOP going to support read across? So we can understand in terms of chemistry, we can understand we may have some mechanism of action. We can use the AOP framework to define the mechanisms of action. And then in future, the theory is to use information from key assays to support in silico prediction. So if I was interested in fibrosis, if you came to me and I said, well, do you have an assay that represents one of those key events in the AOP? And this is quite a well-established process. So what I'm going to talk a little bit about is how we can use the existing knowledge we have to support a read-across argument. And I'm going to talk firstly about strategy and a template, and that will become obvious for read-across. And those of you in the room, this is taken from the paper you have, and I'll explain where that paper comes from in a moment. For those of you online, I'll give you the reference. And at this point, I must say, I must acknowledge the work of Terry Schultz from the University of Tennessee. Many of you will know him. And a lot of the work I'm going to briefly summarize now, I can't claim as my own. Cosmos has certainly contributed to it. I can't claim it as my own, but a lot belongs to Surat 1. Other people indeed in the room, Catherine Marney and people within Cosmetics Europe. Cosmos contributed to in silico evaluation. Colleagues here in Liverpool and elsewhere in Cosmos did a lot of work collecting the data to support the arguments, and we helped in manuscript preparation. And some of this work was performed externally to Surat and was supported by Cosmetics Europe, and we hope that it will move forward. And what I'm going to talk about now, to me, is one of the most important things that comes out of all of this research, and one of the least interesting. It is purely paperwork in many ways and developing a scientific and intellectual argument. It's not exciting, groundbreaking research. It's saying what you've done and recording it. So it is important, but it probably won't keep you awake at night buzzing with excitement, but it is essential. So I'm just going to very briefly outline a piece of work that was undertaken, led by Terry Schultz, with a lot of collaborators from Cosmetics Europe and the Joint Research Centre. And we were involved a little bit, and the University of Tübingen, and we were involved particularly in the manuscript preparation. This paper in Regulatory Toxicology and Pharmacology is available open access. And one of the aspects here was to develop a framework to perform read across. And there's already a lot written about read across, both at ECHA, OECD, US EPA level, and we use this to inform what we were doing. So we developed a way, or tried to describe similarity in a transparent manner. So the similarity between molecules or between groupings. We tried to define ways to document the logic leading to a prediction so it can be recreated by a third person. And that's important for regulatory acceptance. We've begun, we believe, to define and characterize uncertainty, at least say where the uncertainty arises from, and clarify endpoint specific and endpoint non-specific factors in the assessment. So for skin sensitization, an endpoint specific factor may be whether it passes through the skin and so forth. We've used 3 broad criteria to assist in defining category membership: chemical similarity and various aspects of chemical similarity in terms of the phys-chem props, the similarity of substituents and molecular similarity. We've looked at what's been termed biological or toxicological similarity, so being able to classify or define similarity in terms of a mechanism of action, possibly relating to AOPs, and whether we have in vitro data to support that, which is important. And finally, in terms of toxicokinetics and biomodifications, is the similarity in terms of metabolic pathways or activation or degradation. And the paper also sets out a way, a template, a series of templates to document a read across. Under these particular headings, statement of the regulatory endpoint, so saying what you're trying to predict, statement of the read across hypothesis. As you'll see, we have some particular hypotheses in the case studies, then stating what the substances are and recording all of relevant data, ending up with statements of uncertainty and a conclusion. So within this paper, there is a particular way of documenting the read across as is proposed. And to support that, this has been presented as a workflow for performing read across. To ensure that you have met all of these issues, then you would undertake the read across by defining what you're trying to do and the substances, describing the analogues in terms of domains, justification of membership, issues with impurity, describing the data matrices, defining uncertainty and so forth. And in order to help you with that, the paper includes a series of templates, and this is 6 of the templates for recording information about the category, and these are at the end. These are available as Word files, and the Word files are available through ToxBank or through the paper itself. So this gives you an opportunity to capture the information associated with a particular category. And it forces you or allows you or gives you a structure to record that information about your category. Also templates to record uncertainty, again asking you to define the uncertainty. So the first uncertainty parameter is the substance identification. Then we go on to phys-chem props, and allows you to assign some, in some ways arbitrary, level of confidence or uncertainty and strength of evidence to each of these particular categories. Go on to a further table for the uncertainties associated with mechanistic understanding. So you're led through the chemistry, defining uncertainties, and then the biology, if you want to think of it in those terms. So the paper sets out a framework for doing this, gives you the template, which is fine in theory. So we need some case studies to illustrate this, and I'm just going to very briefly outline what's gone on in the SURAT1 case studies, and some of the personal, and I would stress they're personal opinions. If I make an opinion, it's my own. It doesn't necessarily belong to SURAT or Cosmetics Europe. So the aims of the case studies were really to put in place that strategy, workflow and documentation template to see whether we could make a read across argument. And also, can we use more data, the so-called new approach data to support read across. So at the start, I showed my clumsy example with the fibrosis and saying this relates to an AOP, and I said, well, wouldn't it be wonderful if we could get information from assays within the AOP? And this is the start of seeing whether we can do that. But we don't have assays for AOPs. We're looking at literature data and whatever else we can get the hand on at the moment. And at the end, we've got 4 case studies, as we'll see, where we'll document and we'll produce arguments. And the intention is that these will end up as publication quality documents following the framework. And the first, as you'll see, is almost complete. And if I could ever find some time, it would be complete. So we have 4 read-across case studies, and there's a paper in Press in Environmental Health Perspectives from Elizabeth Berger and as first author, and a number of others, which outlines the rationale for these 4 types of case studies. That's, again, freely available, Environmental Health Perspectives. I'll briefly outline them to you, and these were agreed upon by a committee within SURAT, bringing in external expertise. So the first scenario is chemicals that do not require metabolism, so they're direct-acting toxicants with a similar mode of action. And I'm going to very briefly illustrate that with the perfluorinated acids. Second type of read-across scenario is chemicals metabolized, the same toxicant, so these may be slightly different in structure, but metabolized to a similar common toxic compound with the same or similar mode of action. That is being undertaken with reactive beta unsaturated alcohols. Importantly, one that's ongoing at the moment, we're almost at the end of it in terms of data analysis, is chemicals with low or no toxicity. So there's no reactive or very specific mode of action that's obvious, and we've looked at the saturated alcohols there. And finally, grouping, which is probably your worst nightmare, similar compounds but with a variation in modes of action. And we're looking at the alkyl substituted phenols. And I should also say there are other initiatives going on that may be industry-led. So this is just 4 particular case studies within this umbrella, and there are other read-across case studies. I'm just going to very briefly outline the results or the findings for perfluorinated alkyl acids. And I've got this, I'm going to do this in a couple of minutes, hopefully. And if I say the document for this report was over 15,000 words, I'm not sure that included even the data. So the document supporting this was enormous, over 15,000 words. I can't tell you how many data we've put in that document, hundreds of pieces of data and information. So what you see here is a very limited summary of it. But it just shows we filled these templates. And the group we're looking at is 7 perfluorinated acids. So these just vary in chain length. And these are known to be direct-acting toxicants. They're not metabolized, they're heavily fluorinated, so they're very unlikely to be metabolized. So in this slide, this just shows we've obtained some of the data, the PhysChem props for them. And I'm not going to go through those data matrices. There's tables and tables and tables. Some of the uncertainties, what's more important is to think, well, from all of that, what don't we know at the end of the day? One thing was we see variations in activity when we vary chain length. So we restricted to C6 to C12. We saw increase in certainty because for some of it we didn't have in vivo data for all of these compounds, but for those that we did, we saw similarities. And one of the major source of uncertainty is, whilst we're happy that these are direct-acting toxicants, we don't know or we can't confirm the molecular mechanism of action. In this case, the source substance we're reading across from was the fluorooctanoic acid, PFOA. That's well studied. We've got what we believe are reliable data for it, a NOEL value for it, based on liver toxicity. And we're saying there's low uncertainty in being able to use that, so a low uncertainty factor. In terms of mechanistic similarity within that grouping, and remember that grouping is just varying on alkyl chain length, is the mechanistic plausibility of what we assume is PPAR activation as the source of liver toxicity, and also that we see, due to toxicokinetics effectively, a bell-shaped potency curve, so we get a maximum at about C8. And the important thing here, I'm not going to go into the details, but analysing the data has allowed us to identify the weaknesses. So the previous read across would just give you the arguments and say, this is it. And now we're saying, okay, we can quantify where the weaknesses are and the uncertainties are. And that now gives you an opportunity to put in further data to see whether you can reduce uncertainty. So additional data come from a number of places. This is existing data. So there's some toxicogenomic studies which show within the group the compounds tested similarities in the gene induction and gene suppression, which all can be related to liver toxicity. We see there's a in vitro binding set of in vitro binding data which confirm PPAR gamma ligand binding, and some of the information from US EPA ToxCast again confirms, well, we have increasing cytotoxicity. That's inevitable with increasing hydrophobicity, but we do indeed see activity in several classes related to liver toxicity. And as we've surmised from some of the in vivo data, the PFOA had the greatest evidence. So this in itself, this slide is not a read-across argument, but it's supporting our understanding and it's helping to lower our uncertainty. We've identified where we have weaknesses, and now we've gone to the literature, pulled the literature together to help us understand those weaknesses and also reduce uncertainty. We've backed up, using some of the software you've seen, we've backed up the read-across arguments using in silico approaches where we do get evidence of PPAR gamma binding. So overall, and bear in mind that is an enormous amount of person-months work, that's a 15 to 20,000 word document I've just summarised, but what we were able to do therefore is say in part at least that the new methods data do reduce uncertainty. And the reason they do that is that they give us confirmation of mechanism of action, and even an insight into that we wouldn't have got directly from the in vivo data. And we also see, I mentioned the possibility of a bell-shaped curve with potency, and that may be something that is also supported by the new approach type data. So conclusion of the read-across study, using the most potent analogue, that the PFOA, as the source substance, as we believe we have suitable high quality in data for it, we can understand that the NOEL value, how it's driven, the effect, and we can use that to read across to other members of the category. So what this study is giving you is an approach to prove that there is evidence that you can group the molecules together and interpolate information within that particular category. So that's the first of 4 case studies. That's the most advanced. There is an extensive report that's been circulated within Cosmetics Europe. We're writing that up for publication, and that should be submitted to regulatory toxicology and pharmacology, where the first paper is. The remaining 3 case studies are in varying stages of completion. The saturated alcohols is almost complete. It's been reviewed internally and externally, and the report needs to be finalized. And the further 2 case studies will be presented and be published. The aim is to get these published within certainly the next, let's be generous, 12 months, but considerably before then. And these will form in part the basis of a dissemination event that will be taking place at ECHA in Helsinki sometime next year. The data is still not quite finalized. So I just want to, in conclusion, this study was nothing that we ever anticipated what would happen when we thought of Cosmos. But what we've used is the Cosmos database, the Cosmos data approaches and tools, and the Cosmos philosophy to bring together a lot of information and demonstrate, at least partially, that read across provides a solution to the prediction of toxicity of complex toxicities. Again, this has been done in the context of SURAT1 and various initiatives, and particularly the work by Terry Schultz and funded by Cosmetics Europe has provided the now published workflow to undertake a read across, templates to support it, and the case studies. And in a way, this is very much still work in progress. This is not complete. We still need to get the learnings from the case studies. So if you were to ask me, is this now in a situation, or is this now something we could submit to ECHA, I can't answer that definitively. It's still something we need to reflect on when the information from the read across case studies is complete. So this brings together a lot of the chemistry-based knowledge and structure activity and data compilation we have. Are there any questions in the room in the first instance?
It's Steve from Unilever again. In that example, Mark, you put up that the recommendation is that you can read across from that particular compound with an uncertainty factor of 1, which I quite like to see. I just wondered, with any of the other case studies, or have the group considered when an uncertainty factor different to 1 may be sensibly applied to read across? Because kind of just thinking back and examples that we've come across, there's always the tendency to, when you rely on some sort of in silico approach, take a sometimes overly precautious view and apply additional uncertainty factors, assessment factors, just to try and give you a bit of a warmer sense and feeling.
Off the top of my head, I can't remember the answer to that. I'm not sure whether we've got that far with interpreting. Can you, Catherine, may be able to shed some more light on that? I apologise.
Well, I can shed just a quick glimpse of light. So we discussed that a bit on page 594 of the publication. I'm looking at it, hence I'm reminded. And we talked about the different uncertainty factors that one could apply, and we settled on 1, 3 or 10 as a pragmatic and usable solution, but recognising that that would be a situation that we'd need to sort of continue to look at over time.
I think, yeah, that there is a number of ways in which we can assign uncertainty. So you can say, I've got the, yeah. You can say 1, 2, 3, you can say put it in a less linear scale, and we're in the process of assigning the uncertainty values in that way for the other case studies.